Okay, so let's explore in these last couple of videos I want to make about these phenomena. Uh, Paddle triangles of a family of rotating equilaterals, as we've been doing in most of our videos, uh, with respect to a point P somewhere on the plane. So let's start with a very well-known construction, which is if you place P on the circumcircle of a triangle and you compute a paddle triangle, that's going to be a set of three collinear points, and the line that passes through these points is known as the Simpson line or the Wallace-Simpson line, and folks have been writing about this for at least 200 years. Okay, maybe not 200, maybe 150. Would have to look it up. Okay, so the paddle of a triangle with respect to a point on a circumcircle is always a line. By the way, this triangle can be any triangle. It doesn't have to be an equilateral, right? So the paddle is always a straight line, provided P is on the circumcircle, which is not the case here, okay? And I actually don't have a way to implement that in this particular app. So let's go back to our family of equilaterals turning about their centroid. Okay, so first thing we can ask is, well, this is a pretty degenerate family, but can I compute, for example, what x1 of this family is doing over my rotating equilaterals? Is doing this nice, seemingly symmetric teardrop object here, right? So if I let's place P on the first quadrant, and you can see that I have this teardrop object that passes through P, and it has a cusp at P, and it touches the inner cosset. Now, the incircle. Usually I don't expect x1 to be doing anything very pleasant. Occasionally we'll do an ellipse or conic, but very rare. Okay, now let's look at what x2 is doing. Okay, so right here we have a pretty nice phenomenon, which is x2 is stationary at a point on the incircle, which is the midpoint between P and the center. If I actually place P on the incircle, let's place P on the incircle, what happens? So now P is on the incircle. Again, incredibly, x2 is still stationary as the midpoint of P and the common center. What if I place P somewhere else? Okay, let's go ahead and release P, and I can place P, for example, at this intermediate state here, and I will notice that incredibly x2 is stationary as well. And if I place P outside of my triangle, of my circumcircle, I continue to have the same property over Poncelet, where x2 is at the midpoint of P in the center. So of course, the locus of x2 over all P, and I can draw that, is going to be a circle, okay? Because if I'm actually moving P along a circle, concentric circle, okay, x2 is going to be the midpoint, and the locus over all P is going to be a circle. Okay, so that's observation number one. Let's turn this off, and now let's look at what's happening with x3. So let's go back to our, before I go to x3, let's now apply an affine transformation to the system to see what happens to the locus of x2. So as I apply an affine transformation, and now that P is outside of the Steiner ellipse, I can see here that this is a non-conic. We saw this in the previous video, that this is likely a cardioid-like curve, right, if I scale this up. And overall P, this thing is probably spanning a family of either Pascal-Limassons or cardioids, right? The cardioid is one type of Pascal-Limasson. Okay, now what if P is actually on the outer ellipse? Still not a conic, not interesting. What if P is on the inner ellipse? Still not a conic. So x2, let's actually just stop right here with x2, and now let's go back to our default situation where I was talking about a family of equilaterals, and x2 was always stationary regardless of where P was, at the midpoint between the center and P. How about x3? Okay, x3 doesn't like this particular location because our triangle is a degenerate triangle. It's the Simpson line, so I cannot compute x3 properly. Now let's move P outside of the outer circle to see if we get something more cogent. So right here, now look at this. This is quite a nice result. The locus of x3 of my paddle family with respect to a point P, which is exterior to my circumcircle, is a circle. That's quite nice. Let's move P now to the interior of the circumcircle. What do I get? A circle as well. So this almost looks like, you know, an inversion of some kind, because I'm going through this degenerate circle here that is just going to become infinite radius, and then I go through an inversion of that circle and I go over there. And you can see that the center of the circle is along the line that connects P and the common center. Okay? So if I go inside, I remain a circle, and so this is basically a circle through and through. Now let's see if this phenomenon survives post-affine. Okay, now that's quite nice. Scale this up, down. Yes. So it looks like, even though I don't remain a circle, I'm still an ellipse if P is outside, post-affine, and if P is inside, let me actually leave P there. I'm just going to contract P. So P becomes a hyperbola. So it has a phase here that looks like a hyperbola, and my foci are not drawn right, but it looks like there's an area here, and I don't know what that is, and it probably is going to depend on the eccentricity of this pair. But there's a phase here where P is, let's make this guy less eccentric, and ignore these incorrectly drawn foci. They should actually be 90 degrees rotated. But as I move P inwards, further inwards, this thing turns again into an ellipse. So nice, okay? X3 is surviving the affine transformation not as a circle, but as a conic. So we have these two results. They can be proved either independently or in the same package, right? So very nice that the locus of X3 for any P is a circle over my equilateral family. So how about X4? Yeah, can I say that? I know that X2 is stationary and X3 is a circle. So anybody who's on the Euler line, such as X4, X5, X20, at a fixed linear combination of X3 and X2 is going to be a magnified or minified circle. So X4, circle, right? X5 should be a circle as well, and it is. X20, which I can draw here, is going to be a circle as well. So we have this kind of family here. They should be having the exact same phenomena as X3 is. For example, let's look at X4. They should survive affine transformations as, oh, okay. So let's see. All right, so this thing is not invariant. So interestingly, though X3 survives the affine as an ellipse, X4 does not. X4 is a non-conic, X5 is a non-conic, and let's check X20. X20 is a non-conic. What if P is actually on the outer ellipse? Oh, I can't do that. Let's go to X4 or X3. Why is it not letting me do that? Collinear. Is that right? Okay, so yeah, so this is the phenomenon we saw in the video I had just done before, which is yeah, that's quite incredible, right? So go back to the we saw this before, right? So when we are at the equilateral family, no affine transformation, I cannot compute X3. Okay, with P on the circumcircle, I can compute X3. We saw just now if P is outside of it, not on top of the circumcircle. However, if I apply an affine transformation, I can compute X3 because my paddle triangle is no longer the Simpson line, and then you get this other incredible phenomenon whereby the locus of X3 is a straight line. We saw this in the previous video. Now how about the locus of X4? Not a conic, X5 not a conic, and X20 not a conic, should be all the way out here. Okay, fine. So let's say we have explored x3, x4, x5, x20 long enough. I want to quickly explore now x6. So let's go back to our default situation, which is, I'm going to place a 0 here, which is, so I don't know if you're noticing this, right? We have maybe 2 or 3 dimensions that we need to do some exploration in. One of them is what's happening in the equilateral case. Another one is what's happening over different triangle centers, pedals, or antipodals, or Cevians, or anti-Cevians. This is dimension 2. Dimension 3 is what happens if P is somewhere not on either one of these two, the circumcircle or the incircle. Dimension 3. Dimension 4, what happens if I apply an affine? So we have to be very judgmental here, and sometimes we will prune certain directions that might contain phenomena that we're not seeing here. But hopefully this is just giving us a taste of what is possible, right? So, okay, I want to look at x6 now. So this is incredible, right? Let's look at what's happening here. The locus of x6 over equilaterals of my Simpson lines is a circle. And the circle is bitangent. It's internally tangent to both the outer and the inner one. If I move P around, I'm going to get this sort of family of circular loci. That's quite nice, right? Does this guy here survive affine? It does survive affine in the shape of an ellipse, which is no longer bitangent. Okay, that's nice. Let's go back to this state here. Now let's move P in and out of the circumcircle, going outwards. It remains a circle. Oh, that's incredible. So x6 remains a circle for P outside of the circumcircle over these equilaterals, right? Let's move P inwards. And it remains a circle. How do I know? I'm actually saying numerically this guy is a circle. Here's the radius of it. So when I'm on the outer, on the circumcircle, the radius of this locus is a quarter of my circumradius. It must be because it's bitangent here, right? What if I'm actually on the incircle? If my friend Dominique is watching this, he's going to like it because this locus has radius 1/10. So here's an incredible thing, right? We start with, so it's an inherent object with radius 1/10 of the circumradius. What if I'm on the speaker circle, which is the incircle of my medial triangle? Let's go there. I'm still a circle, but I'm a pretty tiny thing, and I don't see anything significant about this radius. So there's two pleasing phenomena here, right? So I have this circular locus of x6 of radius 1/10 over here, and circular locus of x6 with radius a quarter over here. And if I place P anywhere, I remain a circle, okay, and I'm going to have a radius for whichever position P I choose. Now let's see if this phenomenon survives affine transformations. So let's go ahead and apply an affine. Yes, x6 remains an ellipse. If I move P around, I remain an ellipse. That's quite interesting, and that ellipse seems to always be axis parallel to my original ellipse, so it's actually not rotating. Okay. What happens if I move P around now? Let's go outside. I'm still an ellipse. That's nice. What if I go inside? I'm still an ellipse. That's nice, so forth and so on. What if I'm exactly on the inner one? I'm this ellipse. Okay. Very well. So now let's reset and let's look at a couple more phenomena, and I'm going to be done. I want to talk about x13, x14, x15, and x16. Okay, so let's go back to equilaterals. Let's go to now x13. Here's x13, and let's look at what this thing is doing. Over the triangles, P right now, let's put P outside. Oh, it doesn't let me do that because, again, I cannot compute x13 in this location. So let's start with a calmer situation. P is now on the incircle of the family. Let's look at what x13 is doing. It's stationary. Okay. What if I move P around? Let's move P around. So what if I place P here? Also stationary. So that's quite nice. x13 is a stationary point as long as P, and let's animate that, and I can actually now change R going in to see if it remains stationary. Yes, it does. Yes, it does. Now, how about outside of the circumcircle? right here. Now that's awesome, right? Look at what just happened. I have a two-state locus. I'm either a point or I'm a circle. And furthermore, the radius of the circle, provided P is outside of the circumcircle, does not depend on P. It's always going to be the circumradius of the original family over 2, half, right? So if I move P around, okay, let's go ahead and take P a little bit further out. Look at that. That circle continues to have radius half. Okay, so X13 for you, two states. It's either a circle of radius half the circumradius, or as soon as you jump into the circumcircle, it collapses to a point. I've never seen this kind of phenomenon. Either a circle or a point. Incredible. How about X14? X14 will be the opposite of X13. It's going to be a circle. If P is internal to the circumcircle, as we see here, okay, and it's going to be a point if P jumps out. Let's move jump. There you go. And by the way, when I say a point, it's a point which coincides with P. Quite nice. How about X15 and X16? But before we go there, I just want to know if these two phenomena, let's go back to X13, a circle, survive the affine transformation. So let's see if they survive. Non-conic for X13. Even when I'm on the outer, I can't calculate it. Let's go to the inner. Does this thing survive? Non-conic. Okay, so X13 is not surviving the affine. X14 is not surviving the affine either, so that's fine. Let's go back to the default, and now let's look at X15. No affine, right? Let's put this on the outer and go for 15. 15 cannot be computed on the outer either, so let's go to the inner. What is 15 doing? 15 is an inherent circle. That's quite nice. Dominic, here we go again, if you're watching this. If I place P on the in circle, the locus of X15 is a circle of radius now 1/8 of the circumradius. And its center lies on the speaker circle. So I'm drawing the speaker circle here, the incircle of the medial. So if I move P around, you can see that it's going to span that, or P on the incircle. And then if I move P away from the incircle, variable, if I move P away from the incircle, let's place it over here and let's increase its radius. I remain a circle for X15. We know that we cannot compute the circle on the circumcircle, but as soon as I leave, X15 is a point. And it's not, as X13 was, coincident with P, but it is a point nonetheless. So as I animate the family, you see this interesting phenomenon. If P is outside, point. If P is inside, circle, or variable radius. And then if P is exactly on the circumcircle, that radius is an eighth. Okay, how about X16? Should be something opposite. X16 will be stationary, but not coincident with P. If P is internal, how do I know that? I can play around with that, right? I can play around with that. Now, as soon as P jumps out of the circumcircle, can I compute this guy when he is on the circumcircle? No, I cannot. I cannot compute X16. So let's take it out, and let's take it in. It becomes a point. Okay. All right, so that's, oh yeah, so let's just check, just to close it all off, if X15 and X16 phenomena survive the affine distortion. So affine distortion, X16 is a circle, which is a surprise. So X16 is a circle under the affine distortion. How about X15? What if I move, let's go inside here. Let's see if this thing has a dependency on where it is. So it's a circle, a variable radius. What if I go in? Then it becomes a more complicated, perhaps a piecewise circular object, okay, that we're not so interested in. But if P is over here, is that what we just saw? Yeah, so there's a zone here where this guy is a circle, which is probably going to be related to the circumcircle, perhaps, of of this affinely distorted family, and the circumcircle is turning, so there could be some issues. I'm not sure. Okay, how about X15? Does it survive in any way? X15 is also a circle in spite of the affine transformation of variable radius, and then when I exit this space, it becomes more complicated. Okay, guys, so lots and lots and lots of phenomena. I'm going to do one more video to top it all off. It's going to be a series of 12 videos. And I'm going to talk about phenomena in the next video about the antipodal, not the pedal as we saw here, for the same triangle center. So X2, X3, the Euler centers, and then X6, and then 13, 14, 15, 16. So I'll see you on the next video.